Greetings, friends. We have week 7 starting now. So we're going to transition into examples on mirrors, and tomorrow we will begin to look at refraction and lenses in more detail. But before we do, a quick reminder on the schedule for this week. We've got PLC 7 posted. That's going to be due Friday. And it's in its usual quiz format, so hopefully no great issues there. We've got homework 4 is going, and that's going to be due 1 week from today, I think. Is it Tuesday or Wednesday? It's sometime next week. I don't actually remember when I said, so I'm going to just erase that and say next week. I forget which one I said, so it's one of those. And we'll have our corresponding quiz to go along with that on that date. And next, actually, we'll have a group, not a group. We'll have a concept quiz. Let's do a concept quiz tomorrow. So that you can get some practice on mirrors and looking at mirrors in a conceptual way. All right, so we'll do that on Wednesday. So take a look for that. It'll be the usual thing. It'll be up all day, and you can pick your hour during the day and sit down and knock it out. So we've got that going. Hopefully your weekend went well, and you had a safe and prosperous St. Patrick's Day yesterday. Well, at least yesterday, according to my calendar. Whenever you're watching it, might be different. So, what we're going to do is we're going to get going, and I think I'm just going to start off just doing some examples on mirrors. So, we'll take a look at a couple of situations in which we need to figure out the image characteristics, what's happening with the location, the magnification, and the real or virtual. And we'll see if we can just figure out a few things about the images, and we'll be going from there. And we'll pick up tomorrow with refraction. So, in the meantime now, let's do this. And so we have our 3 types of mirrors: plane mirrors and concave, or what I call converging mirrors, and diverging, or which are also called convex mirrors. I don't know if I don't remember saying this for sure, but just in case I didn't, I do use the terminology converging and diverging rather than concave and convex, because it's going to switch when we get to lenses, but converging, diverging doesn't switch, and that's the way I'm going to go with that one. Plane mirrors, I think we've got reasonably well figured out. And then we've got converging and we've got diverging. So the idea with the plane mirror is that the object distance is going to match the image distance, right? So if I'm wondering how far behind the mirror the image is, well, I should measure how far in front of the mirror the object is. And the magnification should be +1, not magnified or minified. It should be same size, and it should be upright, so plus sign. Converging and diverging, now we're going to look at a couple of different cases of these here today and do some ray diagrams. I'm going to go through the 4 rays that we can use in drawing ray diagrams for these types of mirrors. So let's start off with just looking at cases. All right, I'm going to start with an example of an object which is in front of a converging mirror. Now, the other thing to think about when we're doing this is the sign convention. The sign convention, and we'll go through this as we move along, but the sign convention is pretty important because if you sign or miss a sign in the equations, that's going to mess up what you're going to end up with. So I want to make sure that we get our signs and our sign conventions worked out. So we'll be hitting that as we go along through here. So let's take a look at an example here in which I have an object located at, say, 18 centimeters from a converging mirror. Now, the converging mirror is going to have a focal length which, let's suppose the focal length is, we'll start with something that's, say, like 10 centimeters. Well, 18 and 10, I wish I could do something a little better than that. Maybe I should do something more like 12. Let's do 12. When looking at a focal length also has a sign to it. So that if I did not, for some reason, tell you that the converging, I didn't tell you this part of the problem. Maybe I just omit this word here. But I told you that the focal length is plus 12 centimeters. Okay, well, I don't know. Am I doing that thing where I'm writing too small again? Let me see here. I'm going to erase that. I'll rewrite that. So it has a focal length of plus 12 centimeters. As long as I tell you that it's got this positive sign, that means that it's converging. All right? If the focal length is negative, that's going to imply diverging. So that'll be one of our first sign conventions for today. The focal length has to have a sign. And that's how we distinguish the converging mirror, the diverging mirror. Alrighty, so we're going to say that f greater than 0, that's converging. Sorry, I gotta just remind myself to go to the bigger font here. Converging. F less than 0, diverging. Alright. Well, that's kind of an interesting situation because we have a positive or a negative. So that takes care of 2 types of mirrors, but we have 3 types of mirrors here. I wonder what the focal length of a plane mirror is. You might wonder that too. So let's take a look here. Suppose that I have an object at 18 centimeters and the focal length of the mirror is positive 12 centimeters. So right away we know that we are going to draw a ray diagram for a converging mirror because the focal length is positive. So, darn, I forgot my long ruler again. I'm going to go grab one. So let's suppose that I go here and we're going to draw. Well, all right. That doesn't seem quite good enough, does it? Half 1, 2, 3. Half 1, 2, 3. I don't like that. Let me draw that again. All right, so still not very good. All right, so here's our mirror with the positive focal length, and now I've sketched in the optic axis here. What we're going to do then is we're going to take a look at just drawing this out. Now, you can scale these things out and say, oh, I've got 12 centimeters, I'm going to make a centimeter the same as a millimeter, and I'm going to scale it all down by a factor of 10, and that's great, but typically it's just okay to go ahead and draw it out and give the distances reasonable sizes. So for example, if I make my focal length here, okay, so if I say that's my F, then I'm going to say, well, I need twice that to get to the center point, and so halfway, let's say that my object is somewhere about here. right? That will be my distance, that'll be my distance P. All right, so let's do this. All right, so let's go ahead and do this here, where we're going to go 18 centimeters on that. We're going to always draw the ray diagram before bashing out some calculations. All right, this is what I'm going to look for. I want to now talk about, well, let's review sign conventions one more time. So the object distance is positive, which is typical for us to put it on the left side of the mirror and then have the light go left to right, bounce off the mirror, and come back right to left. The focal point is positive. What that means is when you're looking at this sign convention here, what that means is the focal length is in front of the curved part. Okay, so when we have the diverging mirror this way, the focal length is on the other side of it where no light is, and that's why it's going to be a negative. Just mentality-wise, we're looking at a converging mirror with a positive focal length and an object that's outside the focal length. Therefore, we should be expecting a real image here. I should be expecting an image that is going to be on the same side of the mirror as the object. In other words, positive image distance. We're going to look at something that's probably going to be flipped over, and whether or not it's magnified or not, hard to tell, but who knows? We'll see how we go. All right? So there are 4 rays now. I mentioned last time that there were 4 principal rays, and I showed you 2 of them. And one of them involved going directly towards what I call the vertex point, which is here, where the optic axis intersects the mirror. And the other point, C, which is the center of the circle that you would have put the needle of your compass in order to make the arc of the mirror. The C point should be somewhere back over here. If I'm careful, I can actually go ahead and find where it is. It should be right about there or so. I think the C point is maybe right around here. It's approximately 2 times. About 2 times the focal length should be the center point. 1, 2, 3, 4.5. 1, 2, 3, 4.5. No, I missed it. It should be more like here. Okay. So we talked about those 2 rays. I'm going to give you 2 more, and we'll look at why they are helpful. So let's write them down here, actually, as I do this. We're going to look at principal rays here. We have the vertex ray. We have the center ray. And now I'm going to add 2 more, and they involve the focal point. All right, so it's parallel in. Focal point out. And focal point in. Parallel out. So these are our 4 rays. I'm going to add these 2, and because they are ones that we haven't worked with, I'm going to draw them first. So let's take a look. If I'm going to go parallel in, go down through the focal point, this is going to mimic the action of an object that is very far away and would have parallel incoming rays. We know that for a converging mirror, when you have parallel incoming rays, and when I say parallel, I'm talking parallel with the optic axis here. It's parallel incoming rays. They are going to converge at the focal point. Therefore, if I pick the one light ray that's coming from the object that happens to be going directly parallel, that one light ray is going to go down through the focal point because that's what parallel light rays do. So I'm going to take this one ray here. It's going to come in that way, okay? And it's going to go out through the focal point, which means it's going to go like this. down there, like so. Okay. Now, I'm going to use the reversibility of light paths to say that had I put a light source directly at the focal point, then what would happen? If I have a light source at the focal point, then when the light rays go out, hit the mirror, and then bounce off, what are they doing? They're coming out this way, bouncing off, and going out directly parallel with the axis. In other words, we have created a lighthouse, right? The beam of the lighthouse is such that, if sometimes it's made of mirrors, not usually, but it's sometimes made of mirrors. So if I had a candle and a light and a mirror like this and they were just rotating around, I would want the candle to be at the focal point of the mirror such that I could cast a parallel beam of light going out that way. In other words, light coming from the focal point will hit the mirror and go out parallel with the axis in the exact reverse of this. All right, so we'll draw that one. Like this. I'm going to go from the object, I'm going to pick the ray that goes straight through the focal point and hits the mirror, which comes this way, like that, and that's going to be the ray going this way. And now it's going to come out parallel with the axis, like this, and you'll notice it's going to cross the one that's coming down through the focal point because these are going to be converging rays. All right, so it's going to come out like so. And here is where they're going to converge. Okay. All right, this would be my image point here then. I draw those two rays to indicate that they are very useful, and I'll show you why in just a minute. That's my image that's located right there. It's apparently, according to my rough drawing here, and it's still rough even though I use a straight edge, it is located outside the center point, and that means it's further away from the mirror than double the focal length, right? Because the center point is 2 focal lengths. It is inverted as we expected. Light rays are converging there. It is a real image. And it appears, because I made my object 1 square high on my board here, this is greater than 1 square high, so I would say that that is a magnified image. Again, that's usually the one that is the hardest to judge, just from a ray diagram, but this one looks bigger and in fact is larger, so as long as I didn't mess up too badly, we'll fingers crossed, and we'll go for a magnified image. So if I take a look at this and I write down my 4 characteristics, what are the answers to the 4 questions? The answers to the 4 questions would be exactly what we just said. I've got a real image, because remember, light is actually converging to that point and making that image. That's real. What else did we say? It's located in front of the mirror. It is inverted. And it appears to be magnified. Okay. Now, this is the situation with just these 2 rays here. What about these 2 other rays here that I talked about? Why not draw those? Well, it's going to make the drawing a little bit more cluttered, but it's going to be maybe useful to see where they are and just remind you of what they do. So let's I'm going to put in the vertex ray first. The vertex ray is the one which comes in here and hits there, like like so. Whoops. All right, let's try that again. Vertex ray comes in like so. Okay, and it's going to go out like so. That's the vertex ray coming out that way. And so, not too bad. It does kind of cross just about where I'd want it to. It does seem to reinforce this is the image point. You do only need 2 rays, and I've gone above and beyond here for you and given you 4 rays for you to choose from. The center point ray is going to be a little bit harder in this case because the way I've drawn this is that the object is fairly close to the center point. Whenever you have a point that you want to draw rays through or from, and it's close to the object, this makes things a little tougher because the angles get steeper. Remember that we're in geometric optics, which means we are supposed to be dealing with shallow angles. So the center point one is the one that I think in this case is going to work out the least best. The focal length and the vertex ones should work out the best in these cases where I have an object that's far away from both the focal length and the vertex. Here though, the center point is kind of close, and it's going to be a situation where I'm going to be going up pretty steeply like this. So if I drew the center ray, it would be going up there. It would be hitting the mirror and then coming straight back along its path. So all I have to do is really just extend this line backwards to see about where it should be going. And it would be going there. And it is missing. You can see that, well, I don't know if you can see, but just in case you can, it hits here instead of there. So, not the best part, but it'll be close enough for government work. Point is that once you have 2 of these crossing and you have your real image established, the others are just basically gravy on the cake just to make sure that, yeah, that's the point. Or at least they're close enough. Alrighty, so those are the 4 rays. And you are free to choose whichever set works best. Okay, so given this, let's go ahead and see if we can, number 1, find out where is the image. We're going to hit it with the mirror equation and find out mathematically what numbers are representing our drawing here. All right, so our mirror equation, now that we've gone through drawing the ray diagram, answering the 4 questions, we go to the mirror equation, which tells us that all we have to do is take reciprocals of these numbers and add them together. I'm going to want to solve for the q, that's the image distance, so I'm going to throw 1 over p onto the other side, like so. And now I'm going to go ahead and solve. I'm going to have 1 over 20. No, I'm not. It's not 20. What did I say the focal length was? 12. It's 1 over 12, and that 12 is positive. And I'm going to subtract 1 over 18, like that. So I think you can see that this is a 1.5 times. So I could make this, what I could do here is make this thing equal to 1.5 over 18. And now I've got 1.5 over 18 minus 1 over 18, so that should give me 0.5 over 18. And the last step of this equation is typically one that often is easy to forget, and that is to flip it back over, because we are dealing with 1 over the quantity that we're looking for here. Therefore, solving for q means I got to flip that over, and it becomes 18 divided by 1/2, which is 36. And it's positive 36. I was working all in centimeters here, so I'm going to put the centimeter unit there. This is plus 36 centimeters is where the where the image is located. If we take that and compare it to our ray diagram up here, we would know that the focal point is located at 12 centimeters, and the object was here at 18 centimeters, and I drew the
I drew the center point here, which looks a little close, but okay, I put it there at twice the focal distance. 24 centimeters is where the center point is. And my image is definitely past that. Past that, how much, I can't tell, but I do feel at least a good feeling because my image is drawn definitely past 24 centimeters, and my math is working out that, yeah, it's definitely bigger than 24 centimeters. So that's good news. If we were interested in the radius of the mirror, again, we've already talked about this, but the radius of the mirror is twice the focal length. Okay, so that's why I've got this 24 here, because that's the radius of the mirror. The radius of the mirror is 2 focal lengths. And that is basically always true for a single surface. Okay, for any given one surface, the radius is twice the focal, or if you like, focal's half the radius. Okay, let's check the magnification. The magnification, as I'm saying, it should be negative and it should be greater than 1 in magnitude. So let's take a look at the magnification. I'm saying it's inverted and magnified. The magnification, you remember perhaps? It's the image height divided by the object height. But we came up with maybe last class, I think it was last class, we came up with a nifty way of calculating this based on similar triangles, because this is geometrical optics. I'm going to come up with negative q over p for the magnification, because it relates the legs of the triangle just as the magnification relates the opposite legs. It relates the adjacents. We have the negative because we want to think about the optic axis as being kind of the axis that divides positive height from negative height, or at least it gives you a way to reference what the object's height was, and then to say what is it relative to that, because ultimately that's what the magnification is doing. It's telling you what the image's height is compared to the object's height. If it turns out that the image has flipped over, then the image is negative of the object's height. In this case, I'm going to get negative q over p, so that's going to be negative q, which is 36, and p, which is 18. I'm not a mathematician, but that looks like negative 2. Negative is good. 2 is not quite what I thought from my ray diagram. It looked like 1.5, but it's bigger than 1. Let's put it that way. It looked magnified from my ray diagram, so I'll take that. And like I said, this is often the hardest part of the ray diagram to really infer. You typically, when you look at the numbers, right, I couldn't have told you it was 36, and I couldn't have told you it was 2, but I can tell you it should be greater than 24, and that should be greater than 1, or greater than minus 1. So I feel like that's about the level that we should be looking at with the ray diagrams. Try to keep them neat, try to keep them reasonably precise, but understand that unless you are going down to the millimeter to try and get the precision that you want, you're not going to be able to reproduce these numbers with a ray diagram unless you spend hours doing the ray diagrams. And I'm not asking for that. I'm just asking for something that's going to represent what we want. All right? Great, so that is a converging mirror with an object outside the focal point. Let's take a look at a converging mirror with an object inside the focal point. In fact, let's go ahead and maybe what we can do is flip these around, and I can say that the focal length is 18 and the object distance is 12. Maybe we'll do it that way. Let's see what's different. Alrighty, so now we're going to do this, and we're going to do this. I'm going to make that 12, and now that's 18. So The good news is most of the equation stuff isn't going to change, but our ray diagram is definitely going to change. So let's redraw that to start with. And I'm going to include all the points that I did in the last ones. Now here, I'm going to go like that. Here's our axis. Now, in this case, I'm going to mark out a focal point, which is relatively far away compared to the object distance. So I'm going to take and put my focal length somewhere over here, which means that the center point should be somewhere over here. And that's the radius. So the radius is twice the focal. My object is somewhere inside the focal point. Let's put it, say, here. And I'll give you a quick tip on this. When you're going to draw objects that are inside focal points, make them smaller than you would if it was outside the focal point. Reason being, it helps keep the angle from the focal point, the ray from the focal point, it helps keep that angle a little shallower and helps the ray diagram come out a little bit more tasty. Let's see here. I'm going to do this. See if I can go ahead and draw these out. I'm going to go ahead and start with the center point is pretty far away. I'm going to start with the vertex ray. So we're going to go here to here. Like that. So it should look, vertex ray looks something like this. I'm going to go ahead and go from the focal point and come out parallel. I'm going to use this one. I'm going to go, now, hold on a sec. I'm skipping ahead, I'm realizing, because I didn't talk quite about this. So we had those two extra rays that I added on, one that's coming in parallel and going down through the focal point. I could draw that one. It would kind of interfere a little bit with my vertex ray a little bit. The other one was going through the focal point and coming out parallel. But that's not possible here because the focal point's backwards. So remember, instead of going through the focal point, you involve the focal point on the incoming ray, which means it looks like it's coming from the focal point. It's on the same angle as the line from the focal point to the top of the object. So there is a ray of light which is doing this, and I just happen to want to pick that one. It's on the same line as if it came from the focal point itself. So let's go here to there. And I should be careful, this is not really here. So I'm just going to dash that. I'm going to dash that line in right there to let you know that the ray actually starts at the top of the object. It does not come from the focal point. It's coming from the object. It just happens to be on the line connecting them. We're going to come out here, which is going to be parallel now because that involved the focal point. So our ray is going to be outgoing that way. And you'll notice that just from these two rays, if you can kind of see them, which maybe you can, maybe you can't. Sorry about that. So we have one which is going that way and one which is going this way. What that means is these rays are diverging. They're coming out and diverging. What we now need to do as people who are interested in what the image is, we need to now trace those back to find out where is the image, because I want to find out where do the rays cross. The answer is they never do. And therefore I want to answer the question, where does it look like the rays may have crossed? And so let's go find that point. That point, if I take this, well, you know what, I'll start with this one. This one's horizontal, so let's just take this one here. And let's go back. Let's go back like this to there. So I'm going to sketch this one back here, and I'm just going to dash it to help me remember this is not an actual light ray. This is an extension of a light ray path. I'm going to take this one here, do the same thing, and if I'm lucky, right about there, right there. Okay, so this will be the image over here. This means if I take a look at the extension of my optic axis would have come in like this, and therefore the image is going to be here. Right there. Now, we're going to go ahead and answer the 4 questions here. The 4 questions tell me that I had to trace rays behind the mirror. So I guess number 1 is the image is located behind the mirror. Because it's behind the mirror, no light actually exists back there. All the light is on this side of the mirror. There's nothing going on over here. It just looks as if, had we taken the object, stretched it, and put it over there, and then thrown the mirror away, we would have seen the exact same thing. So, since there's no actual light coming from anywhere over here, or any light making this image, it's all this side, right? This must be a virtual image. It does appear to be upright, same orientation as the object, and I will say that this does appear to be magnified, and it should have a pretty good magnification on it. Magnified, there we go. It is magnified, and because my original object was only this big, so this has a magnification of almost 3, it looks like. Okay. Now, with these expectations, I'm going to go back and do my mathematical representation and see how well I did. So same again here, 1 over q. I'm solving for the image distance. So I'm going to begin with the mirror equation, push the 1 over p off to the other side, and that means I got these backwards because I was thinking about them and I wrote them the wrong way. It should be this way, this way. And what's going to happen now is I'm going to put in my values. My object distance was 12 centimeters, but my focal length was 18. So look what happens when I take the reciprocals of these. It's 1 over 18 minus 1 over 12, and that's a smaller number minus a bigger number. My image distance is going to come out negative, but that's okay because I already said it's behind the mirror. Remember the sign convention. The sign convention is if light is on the side of the mirror where you're expecting to see it, if it makes the image over here, then it's a positive image. If it makes the image over here, but there's no light over here, so we call this a negative image distance. Okay. I'm going to do the same trick here. I'm going to say this is 1 over 18. Instead of being 1 over 12, this is 1.5 over 18. And that's going to mean that I've got negative 0.5 over 18, as I did last time. And flipping it over, I'm going to find this is negative 36 centimeters. Surprise, surprise. Now, I can't tell you just by looking if that's 36 centimeters. If I compare it to the focal length, which was, 18, is about there on my diagram. So this is not scaled, but again, it doesn't need to be scaled, but it's showing me good comparisons. The focal distance is definitely less than the image distance, right? If I take this focal distance and I kind of put it over here, so the focal distance is less. So this should be a number that's greater than 18 centimeters, and so good it is. Okay, it's twice, and my diagram's not twice, but all right, I'll take it. Same thing's going to happen with the magnification. We're going to go negative Q divided by P, which is going to work out at negative 36 over 18. Note I have two negatives, and it's going to turn out at positive 2 this time, where I was thinking it was more like 3, possibly. I tried to make this about a half square. It's a little bit bigger than a half square, and that's a little bit bigger than 1.5 squares. So I missed it off a little bit. Nonetheless, it's definitely bigger than, it's bigger than 2. Sorry, it's definitely bigger than 1, is what I was saying, yeah. Alrighty. Good. Questions which you may have about doing this? Magnification should be 3. Oh yeah, thanks. So you are paying attention. 12. So it is 3. Ha! Look at that. I should trust my ray diagrams more. Thank you. Yeah, I forgot. I changed the object distance to 12 instead of 18. Good. So, all right. I feel pretty good about that. All right, so let's see here. That would be the virtual image for the converging mirror. So that means we have one more left, and that will be the diverging mirror. So we're going to go here, and I'm just going to get rid of all of this. And since we know that the focal length of a diverging mirror would be negative, let's suppose that we have an object which is, again, object distance positive, but now we're going to have a mirror with a negative focal length. All right? So object is now at plus 8 centimeters, and this is near a focal mirror. And this will be typical wording of focal length negative 10 centimeters. All right. Focal length negative 10 centimeters. So let's take a look at this. Here is a diverging mirror, and its optic axis is here. I'm going to go ahead and take the liberty of extending the optic axis all the way through. Now, the sign convention indicates that the focal point is on the curved inside, right? In other words, it's on the what we would call the concave side of the convex mirror. Yeah, right. You see why I don't use concave and convex? It's on the opposite side of where we're shining the light. In other words, right, the concave mirror looks like this. So if I tip it this way, you can see it's a dish that's pointed like a bowl, like that. And then simply if I took it over like this, and then I silvered this side of it, like that, this would be the convex side, right? This would be the diverging side. So then you'd get a mirror which looked like this, right? I'd have the mirror like that, I have the shiny side here, and there's the image, okay? So the focal point is on the side which is the curved inside, and we're saying that that's 10 centimeters. And so that means, if I go 1, 2, 3, 4, 5, so that means here is my focal point. Since everything is kind of geared towards light being on the left side of the mirror over here, this is the positive side, so if the focal length is on the other side, focal point is on the other side, I guess you're going to call that negative. Okay. Now, we've got an object which is at 8 centimeters, and I'm going to make it right there. Okay, so that'll be my object, and that's my mirror, and that's my focal point. So now I have to interpret the 4 rays. Which rays do I want to draw? Well, the vertex ray is pretty straightforward. I can certainly draw the vertex ray. What I'm going to do, though, is I'm going to do the 2 ones involving the focal point, because those are a little less straightforward. So I want to show you why they're useful. And I forgot to do this with the converging mirror, so I'll do this now with the diverging mirror, and we'll go back and do it with the converging mirror. Let me show you the focal point rays. The first one is supposed to come in parallel with the optic axis and go out through the focal point. Well, you can see coming in parallel is no problem. Going out through the focal point, though, it's not literally going to go through the focal point, because it's a mirror. And this, again, is also a common mistake that I see, is that people are going to draw this in and have the ray go that way. But it can't go that way because it's a mirror. So we have to figure out, what does it look like if it's coming from the focal point? And what we do is we go like this. We're going to say, well, the light ray comes in straight like this. And when I say straight, I'm really meaning it's parallel with the optic axis. But now it's going to leave the mirror, and this is a diverging mirror, so I know my light rays on this side have to diverge. It's going to leave the mirror along the line as if it was coming from the focal point. Focal point is here, and the mirror is getting hit by the light right there. So what I'm going to do is I'm going to take the line that connects the focal point with that point right there and just go straight along that way. So the light ray is going here, bouncing off and going that way. This dashed line is simply there for my visual ability to draw the light ray on the left side of the mirror. But it'll be there for another good reason as well. And I want to just take a minute to explore what that reason is. The reason to put in the dashed line on this side of the drawing is because, think about for a minute, if I wanted to ask you a question about what happens to the image when I move the object. Question, if I take this object and I scoot it closer to the mirror, what about this ray has changed? The answer is nothing. All I've done is, instead of having the ray start here, it would start over here. But the path would be exactly the same. Likewise, if I said I took the object and I moved it way back here, now I've just got to draw a longer incoming parallel ray, but ultimately the path is still exactly what it shows right here. Why is that interesting? That's interesting because it confines the region where the image is possibly going to be. The reason it does that is because I know I've got a diverging mirror, so I'm expecting diverging light rays over here. I know I'm going to have to trace them back, and here's a light ray that's already traced back. Therefore, wherever I put the object, the image must fall within this area right here, this little triangle, and it's confined by that dashed line. So the closer and closer and closer I scoot the object to the mirror, the closer and closer and closer the image gets to the mirror, And the further and further and further away, the further and further and further in, but it scales down like that with that hypotenuse of that triangle. So this ray is a really useful one. I forgot to point this out in the converging case too, but the same thing is true. When I drew the incoming ray parallel and then going out from the focal length, if I scoot the object around, that ray doesn't change. It just changes where the intersection, if it's a real image, for example, it changes where the intersection of the rays is going to be, and therefore the magnification of it. Likewise here, it just changes the size of the image. But the ray or the line that connects the ray with the focal point, that doesn't change. So your image, you're guaranteed is always in here. Kind of cool. Anyways, so let's take this and go, let's take this and go with the vertex ray. Oh no, I said I was going to do both the focal point. Okay, we'll do this. We'll do the other focal point ray. So this one came in parallel on the left as if it came from a focal point. The next one would have gone through the focal point and come out parallel, but this one's obviously not going to go through the focal point, but it can be angled towards the focal point as if it would go that way. So that means I'm going to take my ruler here and I'm going to connect the focal point with the top of the object. And I'm going to draw like that. That's my incoming ray. Notice though I'm stopping at the mirror. There's no point in continuing this ray towards the focal point. That's just going to cause confusion because the light ray doesn't go there. It hits there and now it comes off parallel. So what I can do, man, this is a good one. Okay, what I can do here is come off parallel. So this ray is going to come out like so and go this way. All right, something I could have said a little bit better with the converging example that we just did, the converging mirror example. These light rays are diverging. So the big piece to this is always look at the outgoing rays. The outgoing rays are diverging. This one's going up like that, and this one's going like that. These are definitely diverging. Okay? These are definitely diverging. And therefore we would have to trace them back in order to find where they might have seemed to have emanated. Sometimes it's very tempting to draw the incoming rays and then extend the incoming rays. You basically never want to do that. I can't imagine a situation right off the top of my head where you'd want to extend the incoming ray to do something. Now, lenses is going to be a little different, but with mirrors, we know the light's all got to be on this side of the mirror. And the light, if it's going that way, never goes past the mirror. So you wouldn't want to extend the incoming rays. What you want to do is extend the outgoing rays. Always concentrate on the outgoing rays and then take those to trace them back. Since I've already got this one traced back because I used the focal point, I'm going to trace back this parallel one here. And I'm going to find that I pick out the part of the triangle here where the image is going to be, and it looks to me like it's going to be right about there, which is small. It's just smaller than the object, which is what we'd expect with a diverging mirror. I could also, for smiles and giggles, just check it with my vertex ray and see if I got approximately what I wanted. Now see, the problem with doing more, I'll do more just so you can see them. Typically, I would advise you use 2, otherwise your diagram is going to get busy like you're about to see, or like you have seen. I'm going to go top of the object to the vertex point here, like that, and then I'm going to come straight out, reflected this way, like so. I'm going to trace that back. That's my outgoing ray. I'm tracing that back. You probably can't quite see that. I did miss it by a little bit, but it's in the ballpark, so it's about there. I wouldn't quibble. Personally, if you're wondering, what happens if you do 3 rays and they don't quite on it? I'm going to do that, so I don't see why you shouldn't be able to do that. Okay, image is here. I'm going to answer my 4 questions. Our 4 questions. The 4 questions involve, where is it? So this one is certainly behind. It is virtual. It is upright. This, however, to my eye is minified. Excuse me. Whereas we had the exact same 3 initial answers with the previous problem, where we did the virtual image and the converging mirror. It was behind, it was virtual, it was upright, but that one was magnified, this one's minified. In general, if it's a single mirror, okay, in other words, if we have just the single component, these 3 always go together. I don't want to say that's always true, but if you have only a single thing, like one mirror, then yes, this is going to be true. As soon as you start including other mirrors, or when we get to lenses, we'll do the same thing. As soon as you get multi-component things, you got to be a little more careful with the absolute rules. But nonetheless, for a single object, these first 3 kind of all group, right? They all track together. If I have a virtual image, you would know it's going to be behind the mirror and it's going to be upright. Yeah. So let's take a look at it with the mathematical pieces here and represent it this way. Again, looking for the image, so solving this for the image point. It's the focal minus the object. I think I got it right this time. In this case, now, I'm going to look at the focal length of the mirror, and I'm going to refer to this. I see in the problem that it is stated as a negative 10 centimeter focal length. That means, right, this is diverging. I do need to keep that sign. When I go into plugging in here, I need that sign in there. That means I'm going to have this thing equal to 1 over negative 10. I have to have that in there. I'm then going to subtract the positive 8, right? This is still plus, so I'm going to subtract 1/8. All right, so it'll look like that. With that, you're assured that the image distance is definitely going to come out negative. It has to, right? And that's what we want. Anytime the image is behind the mirror or virtual, it's got to be a negative image distance. All right, so what would work here? We could do, I guess we could do 40s. Should we do 40s? This is minus 4/40. This is minus 5/40. This is not super tasty, but it's going to come out minus 9/40. Is that right? If I do 5 and 5, that's minus 4 minus 5, so this is minus 9. So this is going to be, what, that's 4 and almost a half, it looks like. Remember, we've got to invert this thing in order to get the Q off. It's almost halfway between, it's a little less, so we'll go 4.4. We'll go negative 4.4 centimeters for the image distance. Negative, good. Right? Light is not over here. I know I keep repeating this. I I won't follow that statement up. I keep repeating this. I do keep repeating this. It is behind the mirror virtual, and let's check the magnification. Magnification, negative Q over P. Remember, it's going to give us two pieces of information. Is it upright or inverted? And that's going to be the plus or minus sign. Is it magnified or minified? And that's the magnitude of the number. Here, in this case, I'm going to get negative, right? Oops, 4.4. And the image distance, I'm sorry, the object distance was 8. So this is going to turn out to be positive. It's not, it's a little less than a half. So it's, say, 0.45. I'll subtract the percent off. It's something like that. Okay. So it's a little less than half of the size of the object, which, boy, that tracks pretty well. I made a 1 square. I'm definitely about a half square right there. It does look, it's about half the size. So I'm pretty pleased with that. The magnification, the height, or not the height, the magnification, it's upright because it's positive. It's a positive magnification, so the image is upright compared to the object. I'll say one other thing about the focal length, which is that the focal length is negative in the diverging mirror. Now, what about the C point? I haven't mentioned the C point. The C point is exactly the same as it was in the converging mirror situation. It's twice far away over here. Here's the C point. I don't know if that quite tracks, but it looks it's about right. And therefore, the radius is 2 times the focal length, but we still have to keep the sign because the radius, right, the compass needle that I put in order to make the arc of the circle here, I put my compass in here and I make the arc. Do people even know what a compass is? I just realized I'm talking about compasses. You probably don't even know what that is. So this is the center of the circle whose arc I am using to be part of the diverging mirror. This is going to be a negative radius. All right, so even though r is still equal to 2f here, radius is still less than 0. Oh, you can't hardly see that. Okay, let me rewrite that. You can't hardly see what I just wrote there. All right. All right, so here's my r, it's equal to 2f, and therefore r is less than 0. This is my C point right here. I'm pointing at the distance from the mirror to the C point. That's radius. Okay. Okay. All right. So we've got ray diagrams, we've got 4 questions, and we've got mirror equation with magnification and stuff like that. All right, the good news about this is that we're going to start, I think we're going to start with lenses tomorrow. Let's see if we have time. We're going to do refraction and then we're going to do some lenses. All of the same essentials will transfer, okay? So we will be able to work with the same equation. There's going to be another one in order to look at slightly different lenses and things like that. But nonetheless, the sign convention should transfer, and the ray diagram should transfer, and the mathematics should mostly transfer. Okay? As long as you're thinking about what should the light be doing, right? With a mirror, the light should be staying on this side of the mirror. Any image formed over here is therefore a positive image distance, because that's what the light should be doing. With a lens, remember, it's going to be going through the lens, and if the image is formed on the opposite side of the lens where the light should be going, that's now, for lenses, that's a positive image distance. We'll talk about that tomorrow. Okay, so let's take a look at, I think we've got time for one more. Let's take a look at one more. Let's go here. Let's go here, and let's start with a little bit of different information in this one. Let's do let's suppose we have an object whose height is known and whose distance is known. Okay, so let's say that we have another example here. Let's suppose we have an object of height being 4 centimeters. And we're going to put that at some distance away from a mirror. And so you have a couple of different options with this, right? Whenever you're using something like this, typically what we do is we're going to know what the focal point is. We're going to be able to know what the object distance is, and so we're looking for the image distance. Certainly the opposite could be true. I could have picked up a mirror off the shelf of a store and been like, what's the focal length of this thing? Right? So if I take an object that's 4 centimeters high, and I know that the distance from the mirror is, say, 15 centimeters, I'm going to end up finding, suppose that the final height of the image, okay, suppose that the final height of the image I can measure the image and say, okay, the image height, h prime, is 5 centimeters. And what's weird is it's flipped over. So what does that mean I need to do to my h prime? I'm going to put a minus in front of there. Okay. So can we figure anything out about the mirror with this little small bit of information? Well, let's see what we can come up with here. If I take, so we know what this is P right here, and I know that I'm going to find the magnification. The magnification is h prime over h, which in this case is negative, and it's going to be 5/4, which is minus 1.25. If I'm interested in finding out what the focal length of the mirror is, I should be able to get to that from here, because I also have the geometric relationship of the magnification to the image and object distances. In other words, this right here. If I take magnification and say, yes, that's also equal to negative q divided by p, but I have what the magnification is, then I should be able to say, I know approximately how big the image distance is going to be compared to the object distance. Therefore, I can take this and say, okay, Q is equal to 1.25 P. All right? When I go back, so in principle right now I could find out what the Q is because I know what P is. I could put 15 in for this. Or I could do it a little bit more slick and I could go into this, I could go straight into the mirror equation and plug in this way. I could say, well, I'm looking for the focal length now, so I'm going to have this plus this. Okay? My Q I know is related to P this way. So really this is like adding 1 over P plus 1 over 1.25 P. And you see now I should in principle be able to find what the focal length is. All I've done is measured the height of my object, measured the height of the image, and I know how far away the object is. And all of a sudden I can find the focal length of the mirror. This is not very much information, but it's extremely useful to find out something about our mirror. Okay? So now, what we're going to do is we can just pop these two together, right? I'm going to do a 1.25 down here and a 1.25 here. We're going to add 1 to it. So this ends up being equal to 2.25 divided by 1.25, and the P is still down here. so that the focal length, if I now flip this over, the focal length is now 1.25 over 2.25 times p. Okay, now, quick sanity check on this, and then I think we're probably just about out of time. The focal length is a number here. That ratio is less than 1. Therefore, the focal length is less than the object distance. Does that make sense? Does it track with what we've been given here? Because notice, I can't really figure out what kind of mirror I have here, so I don't have the ability to start off with a ray diagram, because I don't even know what kind of mirror I have. I could be coming out with a negative focal length here, and I could have assumed it was a converging mirror or something like that. So in these cases, we have to think a little bit more mathematically to start with, which is somewhat unfortunate, but nonetheless, I can now go back and draw this and see if everything tracks. Since we're just running out of time, let me sketch out how I do that. In other words, the focal length is less than the object distance. That means that if I'm going to draw this as a ray diagram, I would come out here and I would say, well, I've got a positive focal distance. Here's my object, but there's the focal length. And therefore, what would I expect from this situation? I would expect a positive image distance, a real image, and an inverted image. Because what's going to happen? Right? I'm going to take this thing this way, go straight down that way, like that. And then I'm going to take the one down through here. It's going to come out through there. My image is going to be here. Like so. I would expect an inverted, magnified image, and in fact that's what I'm getting, as long as the object is outside the focal point. So this seems to track well. The focal point should be less than the object distance in order to make all of this work out. All right. Okay, so what we've got through today, the 3 major ray diagrams for the curved mirrors. We've talked about sign conventions. We've talked about the 4 possible rays that you can use to locate where the image is. And we've also talked about if the rays are converging, you have a real image. If they are diverging, you have to trace them back behind the mirror to find the virtual image. All right? Okay, so with that being said, we're going to transition away from mirrors beginning tomorrow and start looking at refraction and lenses. In the meantime, PLC 7 is up for Friday. Homework 4 is up. We'll have a quiz tomorrow, which I'll enable, and it will be a conceptual quiz, so no calculations should be required. And homework is going to have a regular homework quiz with it, and that's going to be next week. So until then, folks, happy rest of your day. Go reflect your wonderfulness to everyone else in the world. All righty. See you next time.